Right, so we have come to lesson 7. If you notice, we've been covering a lot of stuff under the software quality assurance. This is not only testing, this is not only debugging, this is also the comprehensive quality assurance process as well. Now, in the beginning, we are going through mostly to do with testing techniques, and then we will get into the quality assurance side, and we'll be then covering some of the industry standards like ISO, CMMI, things like that. So last week we looked at one technique known as the black box testing, right? Now for black box testing, if you remember, uh, black box, as it says, is about you don't know what is happening inside the black box, or you don't know what is inside the black box also. So you give the function to someone who doesn't understand the code, who doesn't have access to the code under black box testing, right? So, but when it comes to white box testing, it's the opposite. White box testing is done by people who have some idea about the source code. So generally, it's either done by your peers, your people working in the same team, or the seniors who are attached to the team. Say, for example, there are people who do code reviews. So they go through your code to look at, let's say, your comments or complexity of the code and things like that. Now, both of them are very much required. Now, black box will test whether you output when you give certain input according to the plan. Whereas white box will make sure you write the proper code, like less complicated, efficient code, so that maintaining will be much more easier later. That's the job of white box testing technique. In a nutshell, this is what we can say about white box. So white box testing is used to test the program code. All right. So the source code structure, and the internal design flow. So three things we are looking at. One is the code itself. We're also looking at the code structure, like the way you have written the code, architecture, things like that. And also the design flow, how the code is flowing from, say, from the login screen to the dashboard, and then, to the actions and whatnot. So, like I said, this must be done by someone who understands code, right? Now, we also need to sort of classify this and see what exactly is going on here, right? In the white box, let me move this away. Program source code is tested without running it, right? Not the binaries or executable. We only need to examine the review the code. It means that we need not execute the code. So in black box, we ran the code, isn't it? We ran the code, we gave the input, then we compared the output with the expected output. Whereas in white box, we don't need to run the code. We are only looking at the code. We are reviewing the code. Yes, so we don't need to run it. So the objective here is to make sure the code works according to the functional requirements. And also, remember, in the earlier weeks, we looked at a code template for the organization, like how you rename the variables, how you name the functions, all that stuff, right? So whether the code is written in accordance with the design developed earlier in the project lifecycle. So we agree on a certain, let's say the company has a certain standard. Project might also has a certain standard. So reviewer need to check and see whether the code that is given to him or her is in accordance with these standards. And also there may be, lots of different functions. Are all functions written properly? Are these functions called? Right? Now there is something called code coverage. We'll be looking at that. And are there any redundant code? Meaning, are there any code that is there but we never run it? Yeah. So we can run various reports to find these things out. These are called redundant code. And also, what about the errors? Are the errors being handled properly? Are we calling the errors properly? Right? So those are the reviews here. Now you see, we don't need to run the code to most of these things, right? We don't need to run. We are checking the source code, basically. There are two common types when it comes to white box testing. One is called the control flow testing, and the other one is called the data flow testing. Now, under control flow, we are looking at where you are starting the program and what is going on step by step, right? Of course, we have lots of branches and modules and things like that. So these conditions are also tested. Now, for example, you may have a branch. Let's say you have an if-then statement. So if true is one branch, if false is another branch. Yeah. So we have to see whether both of them are called under certain conditions. So if the false condition is not getting called ever, then you have redundant code. So we need to check that. That is called control flow testing. Data flow testing is where you make sure the data variables are properly covered. So you need to have coming from the black box testing. Some of these things are coming from the black box, like I said. So whether you're testing the minimum, maximum, are the variable properly declared? Now, for example, as you go forward, I'll show you. Now, we are trying to accumulate value to a variable. And if the variable is not initialized, we will have some serious trouble there. So two ways of testing, white box testing, right? If you look at it from a diagram view, so we have static testing and dynamic testing, right? Static testing is what we looked at just now, where you do something called code walkthrough and code inspection. Code inspection is where you look at the code, try to understand whether indentation and certain classes, if you are using, are they properly permission is given to method and things like this. That is code inspection. Walkthrough is part of that, where you go from line 1 to end of the line. You go line by line to understand whether the code is properly running or rather properly written, because you're not running the code here. But we do run it as well. So when you're running it, that becomes dynamic testing. So there is something called unit testing, where you take one unit at a time. The unit can be one function or a one module. So generally, when you say unit testing, we talk about one function. So you can write a function test code separately and then run that to see whether it is working properly, right? And then unit coverage is where you need to see whether all the lines you are having, are they called? Do you have any unused lines? Do you have, you can in fact get a count, like how many comment lines do you have? How many executable lines you have? Then you can in fact have a percentage of that, right? Out of 100 lines, how many lines are code? How many lines are comments? How many lines are called? How many lines are not called? Things like that. And the third one is very interesting. Code complexity. How do you define that? Who can say this is complex and this is not complex? There's a scientific way of doing that. We'll see that also, right? Now, all these things come under white box testing. Now, since we talked about the static earlier, let's talk about the dynamic white box testing technique. First is called the unit or functional testing. Now, this is very simple, and we've been using it anyways, right? You write a little piece of code, and then you have maybe a print statement inside that, and you run it. If your print statement is running, you know it's working, right? So that's the absolute basic way of doing it. Now, certain IDEs go beyond that. They give us something called breakpoints, right? Breakpoint. Now, for example, here we have an example. So we have a Java code here, and as you notice, there is a square here, right? The square means there is a breakpoint, so it stops here. So when you run the program, it stops here, and then it gives you a new menu, bunch of menus, so that you can observe and see what is going on with your program. So this is called unit testing or functional testing. Let me quickly show you. I wrote a simple program with my Netbeans editor. Let's see if I can go there. Yeah. So this is a very simple program. I can minimize the whole thing. So as you notice, here's my tester program. Here I have two functions. One is my main. So main has just two printlns. The first one says Java test. Second one is actually calling the method called sum, which is here, right? So this is another method. So I have two methods now, main method and the sum method. So main method is calling the sum method. Sum method is basically finding the sum of two numbers. So a plus b is a sum, and that is returning. So to check it out, I'm sending 2 and 3, and I should get number 5, isn't it? Because after adding, I should get number 5. So let's see whether it works. I'm going to click this. Yes, I am getting. The program is correct, right? It says Java test and total is 5. All right. Now, if I want to stop this program and then find out what is going on with the code and variables and all that, all I need to do is put a breakpoint somewhere. All right. Now, here, I'm going to put a breakpoint, say, for example, somewhere here. So I'm going to click this. I just clicked on the number, line number 26, and I got a red color square, right? And then the whole line is pink. Let me run this code again now. Now see what happens. When I run it, it is running. Okay, so nothing special happened. So I need to go now back to the top of the line here. And let's see whether I can debug this. All right, debug project. Let me say debug project. Okay, so now the program is running, but I have a new window here. You see, program ran from the top, and now you see there's a little arrow here because in line 26 it stopped, right? And then I have another new window called variables and then also breakpoint. So under breakpoint, it says line tester 26. Variable here, I have something called static here, and also I have some arguments here, right? And nothing much to see here. So, but apart from that, did you notice I also have some other special buttons on the top? So here I have stop debugging. This is to pause. This is to continue. This is to step over expression, step into, step out, run to cursor, apply code changes, stuff like that. So I'm going to step into, because I want to go step by step, right? So now when I press that, it went inside the Java library called the print stream Java. Oh boy, I don't want that. Let's run that. Okay, that program completed. Okay, let me put a break here, right, on this function. Actually, I can put this back. Let me see. I wanted to go step by step. So let's run again. Debug project. Let's go step by step. I'm going to use step into. Right. Let's go here one by one. Okay. Into. Basically, I'm running the Java library now. Okay. So these functions are coming from the Java library. So I have stopped my code, actually paused my code, and I'm running line by line. That is actually too much. It's taking a long time. Okay, I'm gonna stop this. And I'm go back to this. I'm gonna stop this thing, and I'm gonna put a I'm gonna put a breakpoint here. Let's see now what happens, right? So this way I can skip through the println and jump right inside my sum function. Okay, I'm waiting. There you go. Now I have A and B here, right? I also have the value of 2 here, value of 3 here. So these are the values I pass, right? 2 and 3. And I can look at the sum variable. S currently it has not shown here. So in fact, I can add a variable. I can say new watch. I can say S, right? S is here. Right now, S is not known variable in the current context. So it says S is created, but nothing is initialized yet. So I'm going to go inside now to run that. Now see what happens to the S. S became 5. Actually, I don't need this because S is coming here also. After I run line number 17, S has a value of 5. Right? And then I can go inside again and that will run the green color line, which is return S. There. It ran, it came to line number 27. Right? So now it will sort of go on with the one we saw earlier. So what did I just do? I ran the code, and in the runtime, while running the code, I can pause the code to see the variable values. I'm stopping the code without, well, no, I don't use the word stopping. I'm actually pausing the code and observing the variable, which is a major thing, right? I can observe the variable while the program is running. Okay, that's very important. So this is something that we do with white box testing, right? Run the product under a debugger or an integrated development environment. Those tools involve single stepping of instructions and setting breakpoint at any function or instruction. So that's exactly what I did. So using the IDE, I stop the function and I observe the variable. Sometimes when you have a very complex function, you don't know what is not working, right? There may be things that are not working properly. So you need a mechanism to go inside while the code is running, observe the variable and see whether your calculations are correctly running. If not, you need to take some action. Right. Here's another example. This is from Visual Studio, Microsoft, right? For a C# application, I guess. So same thing. You have a breakpoint here, and it is showing what is going on, right? somewhere here that there's a breakpoint. So you can see two breakpoints are here, and then this is called the watch window. So watch window is the most interesting one. You can watch the variable while you are busy, running the code. So these are tools very, very important. Do you notice we are looking at the code? So this is not black box, right? This is white box. Next is called code coverage testing. Now, what does that mean? Now we have a complex code and we need to see whether all lines are run. Some lines are running, some lines are not running. If you have lines that are not running, that's a waste of space, right? And also it'll reduce the speed of the code. So in fact, we show this as a percentage. This is how it works. Total statements exercised. That means how many statements do you have run? Yeah. Divide by total number of executable statements in the program into 100. So this is a percentage. So if your code coverage is 90%, that means 10% of your code is not running. They are redundant. If your code coverage 100%, then your code is efficient. You are running every line there. Now, how do you know that? How do you get it checking? Well, you can go back to the IDE. There are different ways of doing it. So let me remove this thing here. Now, in order to do that in Netbeans, you need to write something called a JUnit test, right? So it's very simple. You just need to go here and say create, test. See, create update test. So when you do that, okay, let me remove this. Right, so I'm going to go here. I'm going to create a test cases automatically. So I'm going to say tools, create test, and then how do I want it? So do you want the initializers, finalizers? I don't think I need any of this. Default method bodies. Yeah, okay, let's see. Right, so under test packages, I'll have my test code. Here, my test code is already generated. Now, this actually fails, so I'm going to comment it. So if I run the test, for example, here, if I click this one, it'll run my code and the test and show me whether my code is passing the test. Let me click all test. Will fail. Open test result window. Oh, it says both tests pass. Very good. So I have a green. Okay, so I have two test cases created and they are running. Okay. Now, there is also something called code coverage. Now, that means, I don't know whether this is running from here. Okay, here we go. Code coverage. I have a red color thing, so it doesn't look like it will generate a report. So if I run a report on my code, yeah, it's not generating. It says no data. Have you run your code yet? Well, I did run my code. Let's see. Yep, coverage is 0. I don't think it's correct. Total line 0, executed 0, partial 0, inferred executed line 0. So let me see this one. Yeah, it's not showing me a report. But the point here is when you have test cases, and your source code, you can run a code coverage test. And then it will generate a report and show you out of this program what is running and what is not running. Now, in our case, we jump here. We also run this, and we pretty much run all the lines here. So this code is good. It runs every line. Okay. Sometimes you might have a line like this. This is not running. This code will never run. Unreachable statement, it already shows that. Yeah. So when you do a code coverage, you will see it there. Now, actually, the IDE is real time doing a code coverage test for me. And so it's showing it to me already that this line will never run. No error. My program is running, but yeah, there is a compilation error. Okay. Unreachable statement. Yes. So this line is having no point having this line. So I'm going to comment it here. So these are the things we can actually do when you have access to the source code, isn't it? And then as a percentage, you can give a report. So as an organization, we need to agree on code coverage percentage. Now, there may be times where you might not be able to achieve 100%. 100% is what you should be looking for, right? So whether you're running it inside your IDE, which is ideal, or outside the IDE, there may be other tools also running some of these report externally. Okay. I just showed you how to do that in Netbeans. There are other tools available. There is Visual Studio Code available. Then there is Eclipse available. Then there are JetBrains available. So each one has a different sort of way of doing this. But well, it's the same purpose. Yeah, same thing. Okay, so under code coverage, which is a very important topic, there are a couple of things we need to look at. One is called branch coverage. Now, when you have if-then statement or switch case statement, you need to make sure that every branch in your decision process is executed, right? If they're not executing, you have redundant code. Number two is function coverage. Now, you might have multiple functions, and some functions are never called, right? Now, as an example, if I go back to our code, oops, let's have another function here, let's say. Public static, static, void, I'll say do nothing, right? This function will be never called. Now see, we never call do nothing function, you see? So when you do a code coverage, you will notice that this function will never work, as in nobody's calling this function. So that's called function coverage. Oops. And then comes the statement coverage. Code is created in a way that every executable statement in the source code is executed at least once, right? So everything has to run. And then loop coverage. So loops we have, and then are we running what is in the loop, right? So that is coming under loop coverage. Condition coverage. What does that mean? Condition coverage, we spoke about it. If then statement, switch cases, all these are whether running, we might also have a default case under switch case, whether they are running at all. And then we have another interesting one called the finite state machine coverage. What does that mean? Finite state mean different state your program is going through, especially when you have a program where you have multiple stable states, right? Say you have a login state. So after login, you go to the, let's say, password forgot state, maybe log in state or log out state, things like that. So does it cover all the states is the next test. By the way, these are tests, okay? Under the code coverage, you can automatically test these things also. There are lots of tools available, by the way, to do that. Now, why are we talking about code coverage so much? Because it's one of the best way to have an understanding about the source code. Number one, it's quantitative, meaning it's very number driven, isn't it? It will give you numbers, percentage wise, various things. Two, it allows introduction of test cases. What does that mean? Test cases. Now you can test your functions one by one, right? And number three is very important. Easy elimination of dead code and errors. What do you mean by dead code? Dead code means the code that never get called. Okay, never get called. Now it talk about testing, by the way. Now I think I need to go back to the code and show you what does it mean. So remember when I created the test cases, I have another new folder called test packages, Java testing, tester, test. Now tester is the class name I have here. So it's using the same class name. Yeah. So here I have two test cases. Each test case start with the at test. See? Right. So all these things are automatically generated. I didn't write a single line of code. And it assumes that I am calling this sum with two variables. So I am testing to see whether after passing two variables, 0 and 0 to my tester.sum, whether I'm getting the answer. So expected result is something and passing is something. So let's say I'm passing 2 plus 4 and my expected result is 6. All right. So if I get 6, my test is fine. If I don't, then I have a problem. So now let's see whether I can test this. Okay, my testing is running here. Right, all pass. Now say, for example, if 2 plus 4, I should get number 5, right? So I'm getting actually the real answer is number 6, but let's say I'm expecting number 5. Let's see whether it works. It should fail now because I'm giving a wrong answer here, right? There you go. It says test sum failed. Expected 5, but was 6. Very simple. It's red. So my function is not returning the property. All I need to do is just correct it here. Right. Now I could have done that here as well under the sum. Yeah. In fact, I can generate. Okay, let's save this. I can go to tools, update test. The existing test class will be updated. Yeah, that's what I want. Let's say, okay, now it will add another new method called test do nothing. Remember that one? Do nothing function. Yeah. So when I call, it does basically nothing. So this is the auto-generated test function. If I run this now, if I test this, basically, it will fail because I have a fail, forced fail here. So I need to comment it. I hope you must have covered this under Java programming, how to write test cases and how to run it. Okay. So this is how you do that with your IDE, very simply. That will pass. Yep, all 3 test cases pass. Very good. Right, now here's an interesting code coverage screenshot I took from Eclipse IDE, right? So here, notice these yellow color lines. It says these yellow color lines are never called and the green color lines are very good. So in the red color ones, they never called actually. So that means I have some redundant code, which I have a problem with. So if I want to increase the efficiency of my code, I should probably remove them. In fact, I don't do that. Normally, we don't delete the line. We need to understand the logic and then we rewrite the logic, right? That is called refactoring. So we just don't go and delete the line because it says never called. We don't do that. Your program will break if you do it. So you have to understand the function and then rewrite it or refactor it in a way so that the code becomes efficient. Okay, that's what we do. Here's a coverage report. Now, if you look at the left-hand side, it says, requirements linked to test and test linked to requirement. 2 sides of the coin. Requirement linked to test. So there are, say, 100 requirements. Out of that, only 42% are linked to tests, meaning we have not written enough tests for our requirements. Not good. Yeah. And test linked to requirements, that means I have 100 tests and out of that only 87% is linked to requirements. That is also bad. Yeah. Bigger the number, better. So by looking at it, we can get an understanding about how good the testing is. Now, when you're writing a complex program, you also need to be writing test cases for each of the functions so that your IDE can automatically test it. This is very important when you are writing web-based application because on the web-based application, you'll be rolling this out automatically using GitHub and Bitbucket and things like that. So the understanding is that these servers will run your tests automatically inside the server. Unlike, me clicking the button here, it'll be run automatically on the server side. Now, here's another sample. I think this is something that we already discussed earlier. So here, we are looking at how to have initial values for our variables, right? Now, since we are using Java, Java has no problem. Java, C# has no problem because the language itself has a specification that says you must have an initial value. So in Java, byte has a value of 0, short has value of 0, int is 0, long is 0, float 0, 0, double 0, 0, character is null character, that is again zeros, boolean is 0, which means false, right? And if you have any reference types, that will be all null. So this is by default from the language. But if you're using a language like, say, C, C++, or PHP, various other languages where the default is not specified by the language, we have some serious trouble. Why we say we serious trouble? Look at this code, right? Here, I say total equals total plus 10. What's wrong with that? What is the value of total in the beginning? Here, nothing. We don't know what the value is, right? So we are creating a variable and we are adding 10 to that variable value. So we don't know what the value is. In computers, when you're starting the computer for the first time, not for the first time, when you're starting the computer, let's say, your computer memory has random values, right? And when you say give me a variable, it will assign that variable to some random place on your RAM. And that RAM has random values. So if you do this, total equals total plus 10, your program have some unpredictable result because we don't know what the total value is. It might be 0, it might be 10, it might be 100. We will have some serious trouble. This is not a problem with Java because the language has the specification saying it is 0. But as programmers, we know this is a problem. So we must avoid it at all cost. Right. Next is called path coverage. What does that mean? Your program runs from one end to another end, isn't it? So while running, there are different paths available like this. See, you can go from A to 1 to 2 by directly going from 1 to 2. You can also go to 1 to 3, then 3 to 4, and 4 to 2 also. Isn't it? So similarly, to go to number 5, you can go to 1, 3, 5 or 1, 3, 4, 5. That is also possible. Similarly, to go to 6, there are different paths available. 1, 2, 6, 1, 3, 4, 2, 6, 1, 3, 5, 6, like that. So path coverage is now you need to have some sort of a percentage and say, okay, I have 100 paths, different ways of going. And out of that, you are only exercising, let's say 50. It's again is a percentage, right? So just like before, total number of paths in the program and total path exercised, right? So your code, how many paths you are actually using versus your actual number of paths, right? Now, by the way, keep this in mind. This is coming back again later. So this circle is called a node and the arrow or the line is called then edge, right? We do some serious calculations later using the node and edges. Right. Next is called condition coverage. What does that mean? Conditions are decision-making condition, isn't it? If then, switch case and stuff like that. So we need to see how many conditions are there. Out of that, how many are being run. So to calculate the total number of conditions, it's actually 2 to the power of number of conditions. So if you have 2 conditions, then you have 4 possibilities, right? Again, like that, like previously, we have total number of decisions in the program, total decisions exercised, and then as a percentage. So sometimes you might have true and false, but then you're not running the false condition, or maybe the true condition, either way, right? So you can only test it by automated some sort of code running. Right, which brings us to another very interesting theory today. This is called the Mccabe cyclomatic complexity. Remember in the my diagram, right? We spoke about complexity of the program. We don't have a way to calculate the complexity, isn't it? So Mccabe came up with a algorithm to calculate the complexity of the program. Now, if you remember, we were trying to, under the code coverage, I said we need to rewrite the code, not just remove things. So when you're rewriting or refactoring, you're also trying to simplify the code because the code is already complex. That's why we have a problem. Complex code means lots of issues and you will sooner or later will end up having lots of bugs, right? So we need to figure out to understand the number. So we need to give a number to the complexity. Is it 1, 2, 500? What is it, right? So I've shared some very interesting videos regarding how to calculate this cyclomatic complexity. The unit is, or rather, we represent it as V in bracket G, right? So how do you calculate it? It's a very simple mechanism. So you calculate control flow graph of the program, right? Like we saw here, right? You take the nodes and the edges. We need that to calculate this. After you calculate it, if your V is 1 to 10, between 1 to 10, your complexity is okay, acceptable. Generally easy to understand and test. If your complexity between 11 to 20, it's bit complex. It's moderately complex. If it is beyond 21 and 50, then it's a very complex program. You might have more bugs and require more testing. Okay. If it is more than 50, extremely complex. Now, this Mccabe cyclomatic complexity is important for the QA team or the testing team. For example, if a developer team comes and say, look, here's our code. How long do you want to test our code? Right? Well, then you can run this. You can run a cyclomatic complexity test and see, right, okay, your complexity level is, say, 1 to 10 or 11 to 20, whatever, and say, okay, because of this, we will need this many days or weeks or whatever, right? That is one side of testing. But on the other side, for code reviewers, this is very important. So if you are getting a number beyond 10, code reviewer must flag it and say, rewrite the code, simplify the code. Right? We call it refactor the code. Yeah. Program is running, but it's very complex. So because it is very complex, it might have many different complicated issues later. Right? So when it comes to cyclomatic complexity, we are looking at coupling between objects, so CBO, right? So what does that mean? It indicates the number of non-inherited classes this class depends on. So say I have a class, right? Let's say it's called sum. And how many other classes I need to work with that is not inherited by me, right? So if I have to work with multiple classes, then it is very complex, isn't it? When it comes to programming languages, in Windows, actually, there is something called dynamic linked library mechanism. This means when you run the program, in the beginning, your exe file is very small. But when it requires a certain function, it will dynamically load another code file from hard disk to memory. If you don't need that function, it will not be loaded. So this was introduced a long time ago because we had a very limited number of RAM. Yeah, so it's okay to keep all the library files on the disk, hard disk, and load only what is required from hard disk to memory. So that's why we call it dynamic linked library. Executor files are pretty simple. They are, independently running programs. So we can just call them with some parameters and it'll do its job, right? Now, when you have strong coupling, meaning you're depending on a lot of files, external files, your program becomes very complex also, right? Now, when you're getting these numbers, okay, complexity numbers, if the number is more than 10, which is high, and the number of methods you have in the program is less than 10, right? Then the class requires factor. Now we can look at a class. This is for code reviewers, by the way, okay? So you're looking at the complexity. Complexity is more than 10, which is high, and the number of methods in that class is less than 10. Okay, then the class requires refactor. If the VG is low and the lack of cohesion is high, then the class is suitable candidate for refactor into 2 or more classes. Now, what does that mean? Cohesion, that is, you have, say, 10 functions, and these 10 functions are not, they can be independent, and they're not depending on each other heavily also. So then you can break that into 2 classes, right? So you can then take whatever you want and then leave your class simple. Right? When the V is high and also CB is also high, which is, coupling between objects is also very high. And then you need to again refactor your class. Or if the CBO is high and lack of cohesion, that means you have lots of functions which are not interconnected and whatnot. Again, you need to look at refactoring. So these are decisions made by the code reviewers. Okay, so by looking at the code, by looking at the theory, looking at the reports, they decide what to refactor. Right, now here's another interesting chart. Now this is called the flow graph. Yeah, so it shows the flow of things from one place to another place. These are common one, like generic one, which you can apply to whatever you are using yourself. So number one is sequence flow graph. One from here goes to the other one. While loop is it goes from here to here, and then this is where we will be asking a question. So if the question is true, we go back here and then come here. Again, go with. So when the question is false, we come to this one here. So similarly, if then else has two paths, right? True and false path, and then come here. Repeat until, again, very similar here. So in this one, we are doing something. When it is false, we come out. Switch statement is where you ask a question and then go through multiple paths, right? Post-test for loop. So here again, very similar to while loop. Pre-test, very similar to repeat until. So we are using this flow to calculate all kinds of different things, right? I have two lessons I want you to go through. That is section 5.1 and 5.4, right? Let's look at 5.1. The book has lots of examples and also how to calculate these things. Yep. Here we go. Right, so here, static versus dynamic white box testing. And if you look at comparing and then calculation, right? So here we go, flow graph example. So it shows how these flow path and nodes are covered and also calculated, right? So I don't want to repeat that in my presentation. Please go through this note to understand how the calculation is done. So here's the cyclomatic complexity explained. If you go further down here, yeah, these are the flow graphs. Right, so here is one. Example 5.1, consider the following code. So I have a function called foo, which is expecting 1, 2, and 3 variables. And inside that, I have another variable with a sign function, and then I have an if else. I also have a for loop, right? So now for us to calculate, let's say anything, we need to break it down into sections. So that's what you're done. So we have 7 sections here. Okay, so these are called flows. 7 floors. And then we write it down like this. So we start from 1, because you have 2 and 3, or 2 or 3. And both of them come to 4. And then it goes to 5, and then there's a loop from 6 to 5, 6 to 5, 6 to 5, and then at the end it's 7, right? 7 is here. Here's a loop. Here's a loop, right? And then it calculates the number, right? And when you look at the complexity, right? There are 3 paths in which program who are independent path, and they form a basis set. So our number, our cyclomatic path is 3. So 3 is not bad, isn't it? It's less than 10. That's how you calculate the cyclomatic complexity. So it's less than 10. So we can say, okay, this code is good. Here's another example. Consider the following program that inputs the marks of 5 subjects of 40 students and output average marks. So we need to calculate the average mark and see how it goes. So go through some of these examples to understand how this thing is calculated. Okay, so let's talk about the midterm exam now.